What is up, ladies and gentlemen? This is a video walkthrough of Slightly Harder, which is on the exam prep discussion. So let's get started. The problem reads, give the runtime of the following functions in theta or big O notation as requested. Your answer should be as simple as possible with no unnecessary leading constants or lower order terms. For F5, your bound should be as tight as possible. Okay, so the first problem, F4, what we see here is that we have if n is equal to 0, we return. Otherwise, we have 4 recursive calls, each to an input size of n over 2, and then we call g of n. Okay, and g of n runs in theta of n squared time. All right, so I think, yeah, when we're approaching these types of recursive tree problems, it's really helpful to draw a tree, kind of a recursive tree. So let's start off by drawing that recursive tree, and then we'll proceed with the same usual kind of true recursive procedure, right? So the first thing we kind of want to do here is we want to say, I want to draw a node for the first recursive call. So the input size to the first call is n, and the amount of work we do is really all in this function g of n, right? What we can kind of see here is this function decomposes into our base case here, our recursive calls, right? So we have our base case, we have our recursive calls, and then we have kind of the work that the function does, right? In this case, f4 just calls some function g that takes theta of n squared time. So what we're going to do here is we could fill in this work to be n squared. So now what's going to happen is that each function call issues 4 recursive calls, right? So what we'll know here is that if we're looking at like an arbitrary one of these function calls, the input size is going to be n over 2. So let's put an n over 2 here. And we know the amount of work that we do. If n is equal to n over 2, we're going to do n over 2 squared work, which is the same as n squared over 4, right? So then we can see here we do n squared over 4 work. And that's going to be the case for all the nodes at this next level. So let's quickly just copy paste those over. And then what we can kind of see here is that here's like, this is, I'd say, the first level of our tree, right? If we're kind of looking at the levels here, this is the first level. And this is the second level, right? So we can say like this is level 0. Let's say this is level 1, right? So I think it's helpful when you're approaching these tree recursive problems. So you try to have around 2 or go up to level 2 in this tree. So let's maybe create another level right now. All right, so let's get rid of this for now. Okay, so we know if we create another level, the input size is going to be n over 4, and we'll do n over 4 squared work, which is the same as n squared over 16, right? So this becomes n squared over 16. And then we're going to have like a ton of nodes at this level, but just to kind of illustrate what's going to happen here, we know that, let's make them a bit smaller. Okay, so we know that each one of these nodes will issue 4 more recursive calls, right? So then each of these have 4 function calls, but for the sake of space, I'm just going to ignore these, right? And just know that this is kind of representative of one of these 3 nodes, right? All right, so now that we've kind of taken this function here and we've drawn the corresponding recursive tree, the next step here is to try to figure out like the work per level, right? So looking at this recursive tree, we've drawn out 3 of the levels so far. So I'm just going to kind of take all of this tree here and then kind of compress it to make it a bit smaller. And now what we're going to do is we're going to create a little column on this left-hand side, and I'm going to call it work per level, right? And if you guys have seen like, I don't know, maybe the first problem or an introductory video, this procedure should be pretty familiar, right? So looking at this top level here, we see that the total amount of work we do on this level is just n squared work, right? I'm just summing the work per node, right? This is the work per node for all the nodes on that level. And then if we're looking at the next level here, we see that we're doing 4 times n squared over 4 work, because we have 4 nodes whose value or whose work is n squared over 4. And we can see that this simplifies to just n squared. And then we'll see on the next level, we have 16 nodes that each do n squared over 16 work. So this also simplifies to n squared. And what we can kind of see in our final sum is that each layer of this tree is going to do n squared work. So we just need to figure out what's the height of this tree. So just kind of looking at this tree, since we divide by 2 every time, then we know this height of this tree is going to be log base 2 of n, right? That's the height of this tree. Let me just try to make it a bit more clear that this is the height. So our total runtime is just the height of this tree, which is log base 2 of n, times the work per level, which is n squared. So it just becomes n squared log n. Right, that's kind of the runtime for the first one. All right, so let's move on to the next one here. All right, so looking at this next one here, what we see is that we have some if statement right here, and we have a for loop. And the function asks for a big O bound, but what we know is that if we're given like a big O bound, we want this bound to be tight. Right? So we're trying to find like a tight big O bound for this function call. All right, so that means we can't just like put what the answer kind of said here. We can't put like some really, really big number, because we know that that's not really a tight bound, right? Or it may not be a tight bound for this problem. All right, so let's try to figure out how much work this function does. So what we can see here is that this function goes from I is equal to 0, I is less than or equal to n mod 10, I plus plus. And then each time what we do is we just kind of recurse on the next node. Or we recurse on n divided by 10 and m divided by 10. Okay, so kind of one observation to make here is that like m doesn't matter, right? Notice that like m is just getting used here, right? M is just getting passed into the next recursive call and it's getting printed. So the first thing we kind of notice is we could just really ignore m, right? It's just going to come down to n. All right, the next thing to kind of notice here is that the number of recursive calls, right? The number of recursive calls is equal to 1 plus the last digit of n. I was going to say the number of n. Okay, so what do I mean by that? Well, notice that this is just the last digit of n, right? If n is something like 959, notice that n mod 10 is just going to be this number 9, right? It's just the last digit. So what we can see here is that since we have an inclusive less than or equal to, the number of recursive calls, or the number of times we kind of call f5 recursively, is going to be equal to 1 plus the last digit of n, right? So since we're kind of concerned about finding a tight big O bound, we want to try to consider like the worst case behavior, right? Or the behavior when f5 takes as much time as possible. So since we're kind of concerned about this behavior when f5 takes as much time as possible, let's consider the case when our given number, or let's say n is defined as a bunch of 9s, right? The reason I've chosen n to be a bunch of 9s is because we want to find the worst case behavior, and we know that the number of recursive calls is equal to 1 plus the last digit of n, right? So what we can see is that 9 is the biggest the last digit of n can be. So in order to maximize the total number of recursive calls, we should consider the number with only 9s. Right, so kind of considering this number, let's look at this recursive tree. So the first time we call our function, let's say it's equal to 900, let's just say n is 9999, okay, just for the sake of example. Then what we're going to do is that, notice that this function call doesn't really do any work, right? Technically, we do like 10 steps here, but we can kind of think that's like a constant amount of work. So I'm just going to put a 1 here, signifying that f5 does a constant amount of work. And another way to kind of convince that to yourself is that we have our base case here, and then we have our recursive calls. right? So unlike the previous example, we had some function g of n that took like n squared amount of time. All we're really doing in F5 is we have a base case, and then we just issue recursive calls, right? So what we're going to see here is that when our last digit is 9, we issue 10 recursive calls, right? So it's going to be 10 recursive calls here. All right, so kind of looking at one of these recursive calls, the input size is going to be 999, right? Because we're just kind of, all that this thing does is just chops off the last digit, right? That's all that this operation does, chops off last digit. So with that in mind, what we'll kind of notice here is that every node on this next layer, right? If this is the top layer, this is the next level, then all of the nodes on this layer slash level, they're all going to kind of look like this, right? They're all exactly the same. So if you want like just to see another visual, they all are going to just have like a 1 in the middle, and we know there's going to be 10 of these nodes here, right? So then what we'll see is that if we look at like the next, there's also going to be 10 nodes here, and each one of these nodes is going to kind of look like right? It's just going to have 2 9s at this point, okay? So kind of looking at this tree that we're developing, what we'll notice is if we're trying to find like this work per level, right, of this tree. So let's create this column, work per level. So looking at this top level, we do 1 work on this top level. So looking at this next level of the tree, we're considering all of these nodes. So since we have like 10 recursive calls and each recursive call does 1 work, then we have 10 work on this next level, right? And then what we'll see here is that this next level is this huge thing right here. So what we'll know is that we had 10 nodes on the previous level, and each one of these nodes issues 10 more recursive calls. So then this next level should have 10 times 10, right? Total number of nodes on this level. So then this is like 100. And what we can kind of see here is that the work on each one of these levels, like if I say that this is, let's just kind of color code it. Let's say this is level 0. Let's say this is level 1, level 2. Notice that this is just equal to 10 to the 0, 10 to the 1, 10 squared. So what we can kind of say is that the work per level is going to be 10 to the level, right? So now if I'm trying to find like the total runtime of this function, what we usually do is we take the sum of this column, right? So one thing to kind of notice here is that sum is going to look like 1 plus 10, let's say plus 10 squared plus 10. And we know the last term here, right? The last term is going to be 10 to the height of this tree. Okay, so the reason for that is this last term is going to be the bottommost level of the tree, right? So if we're kind of considering that this is level 0, level 1, and level 2, the bottommost level of this tree is going to have level height, right? It's the level of the bottommost level. Okay, so maybe that was confusing, but yeah, that's the bottommost level of the tree. Its level number is going to be the height of the tree, right? So what is the height of this tree? So what we'll kind of see here is that as we're going down this tree, what we'll see here is that we're just dividing n by 2 each time, right? So if we're dividing n by 10, right? If we keep dividing n by 10 every time, what we'll notice is that the height of this tree is going to be log base 2 or log base 10 of n. So this is the height of this tree is log base 10 of n. And the reason it's log base 10 of n is usually if we have like this, a tree, like looking at this example here, this tree has a height of log base 2 of n because we keep dividing by 2 every time, right? So now, since we're dividing by 10 every time, and now it's log base 10 of n, right? So if we're looking for the value of this, it's going to be log base 10 of n. And another thing to notice here, as we can kind of just see with this example, is the last term in this sequence dominates all of the other terms, right? So what we know is that this term here dominates the preceding terms. So the total runtime of this function just kind of comes down to what is the simplified value of this term, right? Or what is like the worst case behavior of this function kind of comes down to what's the simplified term. So what we can see here is that this is actually just the same as n, because if you have some function like a log a of n, this is just n. That's just like a log property. So kind of using that log property, we'll see here is 10 to the log base 10 of n simplifies to n. So what we can say is that since the worst case behavior of this function, right, we've defined this to be the worst case behavior of a function. Since that worst case behavior takes us n time, we know that a tight big O bound is tight big O of n, right? So yeah, that's all for this problem. I hope you guys found this video walkthrough helpful and have a good rest of your day.